Hello everyone, my name is B. Satvik. I am from CSE-D section and my roll number is 20951A05G3. Today my tech talk topic for design and analysis of algorithms is topic graph analytics accelerators for conjugative systems. Introduction. Conjugative systems consist of many elements such as natural language processing, artificial intelligence, machine learning, and data analytics. These systems rely on processing large amounts of data. Hence, there are ongoing efforts to integrate big data analytics with conjugative systems. Graph analytics has been gaining popularity recently, especially due to the abundance of data from web and social networks. Especially graph-based large knowledge bases can be used to conjugative systems for reasoning and human interactions. There are many graph algorithms that are executed in the inner loops of conjugative systems. Many speech recognition and language processing models used in conjugative applications can be represented as graphs. Conjugative platforms such as unmanned aerial vehicles UAVs or self-driving cars run single source shortest path algorithms in their inner loop computations. Personalized recommendations can be generated from large data sets using algorithms such as stochastic gradient descent on bipartite graphs. TextRank is a model proposed for natural language applications such as tagging documents with key phrases and sentences extraction for automatic summarization. TextRime operates on graphs where vertices present text unit example terms and edge represent the association inferred from the input text. Graph analytics based conjugative systems are different than traditional compute intensive applications with regular access patterns and abundant data and thread level parallelism, as will be discussed later. Graph applications are hard to parallelize due to irregular execution patterns and synchronization requirements in vPro requirements. Graph analytics applications. Graph analytics applications are among the core algorithms used in conjugative systems. However, implementing these applications on existing systems efficiently is not a trivial task due to several reasons such as memory access, bottleneck, synchronization problems, and irregular computation or communication patterns. As will be discussed shortly, these properties can be exploited to improve performance and power efficiency by hardware consumption. Many graph algorithms are iterative in nature, where execution continues until a convergence criteria is met. However, the number of iterations required to converge individual vertices can be significantly. Our analysis shows that the enabling symmetric convergence decreases the total number of edges processed by 47% on average, while the single instruction multiple data type of architecture can process multiple vertices simultaneously. They too have control divergence issues. When asymmetric convergence is enabled, asynchronous execution, which allows neighbor vertices to access the most recent data, can improve work efficiently. Even further shows the relative number of edges processed per page rank. When we support both asynchronous execution and asymmetric convergence is enabled, as shown here, these features reduce the number of edges processed by 66% on average. However, if a programmer wants to utilize the work efficiency of asynchronous execution, then he or she should handle synchronization and enforce sequential consistency in software to prevent data race conditions. Fine grain locking mechanisms slow down the execution of both CPUs and through output architectures. One of the main bottlenecks in graph applications is memory loss because of low computer communication ratios, low spatial or temporary locality, and hard to predict memory accesses. Some real world graphs, such as social networks, follow power law distribution where a few vertices have higher degrees when compared to rest. In such an environment, static partitioning of vertices to different threads greatly suffer from load imbalances, and efficient implementation needs to distribute its workload carefully, and more importantly, it should be able to handle high degree vertices efficiently. Proposed architecture template. There have been several graph frameworks proposed in last few years. The common objective is to hide the complexities of parallel and distributed software development by providing high-level programming interface. We follow a similar approach for our template architecture, especially use vertex-centric. Think like a vertex abstraction model that consists of gather, apply, scatter functions as in GraphLab. In this model, users need to define basic data structures corresponding to each vertex or edge and implement serial functions for the following up. For instance, gather, collect, and accumulate data from neighboring vertices and edges. Apply, perform the main computation for input vertex using gather results. Scatter, distribute the vertex data in apply to neighbors. Determine whether to schedule the neighboring vertices for future execution. The application specific data and functions in the programming interface are clearly separated from the architecture template implementation. All application specific data structures and functions are defined in plain C language and are plugged into our architecture template. The template automatically removes the hardware corresponding to empty data structures and unused features. The proposed accelerator is loosely coupled with the host processor and it is connected to system DRAM. It is assumed the host processor will populate the graph data in the DRAM and send a start signal to the accelerator. Once the accelerator finishes computation, it will send a signal back to the host. The main features can be summarized as follows. 10 of the vertices and 100 of the edges are processed simultaneously to achieve high levels of memory level parallelism. This is done by maintaining partial states for multiple vertices and edges while waiting for the responses to long latency memory requests. Scale-free gaps are handled through dynamic load balancing. Synchronization between concurrently processed vertices and edges is done in the sync unit module, which is specifically designed for graph processing. This module ensures sequential consistency with negligible performance overhead. Furthermore, it works in a distributed fashion without a centralized bottleneck. The set of active vertices is maintained by the Active List Manager module. This module enables simultaneous high throughput reads and writes from or to the distributed active list data structure without the need for expensive locking mechanisms. The memory subsystem is optimized for space graph data structures. Conclusion. In conclusion, we have proposed an accelerator architecture targeted at graph analytics applications. To follow the well-known gather, apply, scatter abstraction due to irregular memory access patterns in these applications. The performance bottleneck is the system memory bandwidth. We have shown that the proposed accelerators can utilize the bandwidth in a much more power efficient way than multi-core CPUs. Furthermore, the paper's template architecture includes work efficiency features targeting iterative graph applications which lead to performance improvements up to 3 times. Although we have studied fixed function accelerators, it is possible to make the proposed architecture software programmable by replacing the application specific logic with simple processing future work. Another future work is to generalize the proposed architecture beyond the gather, apply, scatter abstraction model. Thank you.